Okay, let's look at how we're going to use this tie line to compute the fraction of each of these phases. So this tie line, as you can see, is a horizontal line, and the endpoints of the line run into these single phase regions. And the original composition creates a fulcrum, which I'm drawing here in green. And the fulcrum essentially divides the line in two segments, a small segment and this longer segment. And the length of these segments are going to tell us essentially the proportion of each of the single phases that are in here. Now, again, the original composition serves as the fulcrum. This is called the lever rule, and let's go through an example at this temperature. So we know that we have gamma plus liquid as the two phases, and we know that the endpoints of the tie line tells us the composition of the phases that we have. So we have on the x-axis weight percent carbon. So this endpoint is roughly 2% carbon for liquid, and then this other one for gamma is roughly 0.8% carbon inside the gamma. So this lever that we've created tells us the proportion of each of these phases. Now the trick is that there's some fancy footwork we need to do. So here's the short segment of the lever, and here is the long segment of the lever arm. And imagine this is actually a balance, and you have a very long moment arm, and then you have a short moment arm. And how would you balance this thing? Well, you'd actually have to put a rather smaller mass here and a larger mass there. So you'd have to put a small mass where there's a long fulcrum, and I'll just draw it in, represent it like this, and you have to put a larger mass on this area where there's a shorter fulcrum. So what this tells you is intuitively, where you have gamma here, you're going to have more gamma than you are going to have liquid. And this makes sense because you can see the fulcrum is, position of it, the fulcrum is closer to the gamma than it is to the liquid. So you'll have more gamma. Now let me write the equation here that we would use. The fraction, so we're calculating the fraction of liquid that we have. And the fraction of liquid is going to equal this. You can see it's a small amount, so it's going to be the shorter segment right here. It's going to be equal to that divided by the whole segment. The shorter, so let's use the numbers 1% minus 0.8%. That would be the short segment, and the long segment is 2% minus 0.8%. That is the lever rule. So again, the liquid we're expecting to be less, so the fraction of the liquid is going to be this short segment over the total length of the lever arm. This reduces to, I don't know what I'm doing here. Notice that the short part it's not exactly intuitive. I'm narrating this because I didn't record it the first time. So it's 0.2 divided by 1.2, and that is equal to 1/6. That fraction is 1/6. And what about the fraction of gamma? Well, it's got to be what's left. It's 5/6. But let's go ahead and prove it to ourselves by computing it. So you can see it's the larger portion. So we're going to, in order to balance this, so we're going to use the larger segment of this lever arm. So the top is equal to is 2% minus 1%. 2% minus 1%. divided by 2%, the whole length, minus 0.8%. 2 minus 0.8, and that's equal to 1 over 1.2, or roughly, or exactly 5/6. So the fraction of gamma is 5/6. The fraction of liquid is 1/6. And you can use this rule anytime you have a two-phase region. And you can also use it in a isothermal transformation for 3 phases. We'll do that in another problem. So let me just summarize here. In a two-phase region, you have a tie line, and the endpoints of this tie line create kind of a lever, and they collide into single-phase regions. You always have single-phase regions on the sides of two-phase regions, and the original composition forms a fulcrum, which breaks the line up into 2 segments. Now let's say you have alpha on this side, beta on this side, so that this endpoint tells you the composition of beta, this endpoint tells you the composition of alpha. And the lever rule allows us to use these composition values to compute the fraction of each of the components that you have in the system, of the single phase components.